Hey folks, my name is James Penick, and I'm going to do a really quick little talk here on how we build out our clusters at Yahoo. So our primary goals are scale and security. And so the reason I'm actually doing this is because I have seen some chatter on mailing lists or kind of had these hallway conversations with folks, and I've heard some folks have struggled with 400 node clusters, 600 node clusters, and it didn't seem like there was really any kind of common information out there. There is no reference build for OpenStack. So I thought if nothing else, I can at least sort of do a data dump on how we build our clusters. Maybe that'll help somebody out. So our global scale is, in terms of VMs, is about, we have 20 clusters globally. Each cluster is an island. And we typically build one cluster per data center for our main production networks, and then for our sort of internal corporate networks, we also have a separate cluster per colo. Our VMs are still globally under 100,000 in total. The most we have per cluster is probably 10,000 or so in a single cluster. The most hypervisors we have in a single cluster is around 1,500. And the VM density changes per cluster. So at the low end, it's 4 to 1. At the high end, it's around 70 plus to 1. So first thing we do is we actually split our clusters up into 3 different VLANs. So if you think about kind of like a mountain, up on top we have a control plane, and in the control plane we have API nodes, database nodes, and queue nodes. Those API nodes, we sort of put almost all things OpenStack are smeared across all of those nodes. So with Nova Scheduler, Nova Network, yes, our VMs are still on Nova Network, sorry. Glance Registry API, all that stuff. They're all on these hosts. They're replicated n times over and over and over again. 2 separate hosted database in the message queue. So that's kind of the top of the mountain. In the middle of the mountain, on a separate network partition, is the hypervisors. And at the bottom of the mountain are the VMs. And they are on a 3rd VLAN entirely. Scaling the database. Okay, this tends to be the first thing we found that fell over, especially if you're running a local conductor and not running the conductor service. So what we did is we took a step back and tried to, based on the amount of load that was going at the database server, we've actually found that a completely unused 200 node cluster with no VMs will actually overwhelm a database if you're using the local conductor. So this is if you're using just a single like 500 gig drive, or even if you're in a RAID 5. So what we do is we just kind of plan ahead, and we use 4 300 gig SAS drives in a RAID 10. That gives us enough IOPS to make sure we can keep up with the flood coming in. 24 gigs of RAM per host. We have 3 per cluster, and load average is about 0.8. So obviously not doing too bad there. This includes the cluster that has 1,500 hypervisors and 10,000-ish VMs. The databases are sitting at about a load of 0.8, so that's not too bad. We use MySQL / MariaDB, depending on the version of Linux we have installed there. We have an internally developed Zookeeper-like thing, but ultimately it's the same sort of thing you see in Zookeeper that does the leader election. Our setup is a multi-master with single writer. And part of what we did that helped us scale is we actually went into all the different services and we identified the places where there are database reads versus writes. Since we're a multi-master single writer, if a writes go to the write master, all reads only go to the read slaves. And so we found that has helped us significantly. Message queue is kind of the next thing that tends to light on fire, fall down, and sink into the swamp. So this one, the hardware, 24 gigs of RAM, single 500 gig drive. We don't really care. It's a message queue server. With RabbitMQ, everything is in memory anyway. We actually have 6 of these per cluster with master-slave failover. And the enhancement here, same thing we did with the database. Writes go to the write master, reads go to the read slaves. And with this, again, the average load is roughly 1 on the master and 0.1 to 0 on the read slaves. Hypervisor, this isn't really a scale issue. I just noticed that a lot of people are pretty cagey about, and I've been one of them, about describing what hardware they use in their hypervisor, or even what the capacity or the depth is. So I figured I'd at least throw something out there. Our hypervisor hardware is all over the map because it depends on what we're doing with it, what our expected density is going to be. It doesn't make sense to buy 500 gigs of RAM if you're going to run really low CPU over commit with VMs that aren't going to be any larger than 34 or 64 gigs. So our production hypervisors lately, we've been increasing our overcommit, so that gives us about 512 gigs of RAM. Some of our older stuff are places in hypervisors in places where we have very low overcommit. They might only have 64 gigs of RAM. We use KVM as the hypervisor on those compute nodes. And then enhancements, nothing really specific. Most of it comes down to the stuff I touched on before with splitting out the database and the message queue reads and writes. So the scheduler tends to be the thing we break the most. My advice is if you are not on Kilo or above, don't be on Kilo or above. If you are like us and you're still back on Juno and you're planning this great leap forward, what you can do in the interim is we found that one of the big problems you have is when you have a ton of available compute nodes. So actually an example of how you can do this, let's say you have 1,500 compute nodes and most of them are pretty heavily used because you have a low overcommit. Well, we bumped our overcommit up. This meant suddenly there was 1,500 compute nodes available and all scheduling requests began to fail. The reason being, in Juno and below, there were a lot of scheduling filters that kept running back to the database and doing more recursive calls again and again and again. Subsequently, it would take so long that scheduling attempts would fail. So one thing we found is that the compute host filter checks the timestamp of the original data call from the database. So, but the problem is that if it's late in the filter chain, what it actually does is it sees the timestamp from when the data was first called, only it's been 2 minutes, so it calls that a timeout. Simplest fix is you move that in the beginning of the chain, everything works again. Now that's a hack. I mean, that's not really a hack, but it doesn't really get you very far. The next thing we did was we backported the in-memory scheduler enhancements from Kilo back into Juno. That got us up and running. Our scheduler was suddenly much, much, much faster. Another thing to be aware of, if you are going to do a big overcommit change when you have, or any overcommit change when you have a ton of compute nodes, you might want to actually split those out into separate AZs and do a per AZ based change and sort of kind of feed things over to let stuff sort of catch up. Ultimately, I would say, though, don't be us, be on Newton when it's available. Just don't be on Juno. So security, this is kind of the last little bit here. Security is a big deal for us. Obviously, it is for all of you as well. Our user trust is a big deal. We want to try and make sure that we limit any attempts at incursion into our network. So the two basic fundamental things we take from here are we practice the principle of least privilege. So this is everything from services to users. So if a hypervisor does not need access to Nova API, we try and prevent that from having access to Nova API. And we also make the assumption that all hypervisors in the network can be compromised. So if you can access a VM, it can be hacked. If a VM can be hacked, therefore the hypervisor can be hacked. And if that means that you now have somebody inside of your network. And we always try and take that perspective. So to mitigate this, the first thing we do is we actually prevent access between hypervisors. They're not allowed to talk to each other at all. So this, of course, breaks live migration. And that's something that we're working on, is figuring out a brokering service in the API layer to allow migration between these hypervisors. But we do not allow them to communicate. Further, we disallow communication between VMs and their hypervisors. So no VM may initiate connectivity to its hypervisor, or vice versa. Not that it really matters as much, but because if you're in the hypervisor, we assume that you're going to be able to talk to all the VMs, but we don't want you to be able to egress out to any of the other VMs in the network. So, and then finally, and this is what I touched on before, again, limit access to only the things that your services should be talking to. So, for example, your hypervisor does not need to talk to Horizon. It doesn't need to talk to a lot of the APIs. Split all that stuff out. So that's it. Hopefully that's helpful to somebody out there. If you have any questions, you can drop me a line, put my email address up there. That's it.